welcome to another one of my IGCSE chemistry videos. Today we're still going to be going over this Unit 1, the particular nature of matter. In the last videos we talked about solids, liquids, and gases. We talked about their structure, in terms of particle separation, how they are arranged. We talked about solids being in a set lattice, liquids being touching but moving, and gases basically not being in contact at all. And today what we're going to talk about is we're going to talk about basically changes of states, how to draw them in graphs, and how to explain them in terms of kinetic particle theory. So we're just going to basically talk about that, and then we're going to move on to the next class through Brownian motion, diffusion, and what evidence of Brownian motion there are. So basically, what our title for this this lesson today is going to be changing. It's going to be changing states. So we need to know the specific, the specific name for all of the different physical phase transitions. So what we're going to be talking about is we're going to be talking about a solid to a liquid to a gas. We're going to be doing the opposite, a gas to a liquid, and a liquid to a solid. And we're also going to talk about a gas directly to a solid, and a solid directly to the gas phase. So with this one, if you've ever seen dry ice at restaurants, sometimes they put Jello into a bowl, they put that into a bigger bowl with some water, and they put some dry ice in there. And what we end up seeing is you end up seeing this white smoke coming out of it. So that's an example of sublimation happening. Was a solid, in this case solid carbon dioxide, is turning into CO2 as a gas. So that's another type of physical phase transition. So basically what we're going to talk about today is we have to talk about the name. So a solid turning to a liquid. We still refer to this as melting. And a liquid to a gas, we always call it boiling. So it might seem a little bit weird, right? We in our lives we talk about melting. If you live in Canada or you lived in Canada like me, melting. We usually always talk about liquid, right? We talk about not liquid, water. So we always talk about water. We've got ice cubes, and ice cubes melt. Snow melts. Basically we talk about it in terms almost entirely of water. But we have to realize that it's not only water. We can talk about metals even. A metal going from a solid to a liquid, the metal starts to melt. We could talk about really anything. We could talk about sugar. If we heat up sugar, we can go from a solid to a liquid sugar phase, and that again is melting. So we need to use that terminology anytime a solid is turning to a liquid, is melting. And same thing for same example here. We got boiling, and usually we talk about boiling water, and we know that water boils at 100 degrees Celsius. So water boils, but also we can boil metals, right? We can heat up liquid metal enough that it starts to boil. So basically we can turn metals into the gas phase. It's just that happens at different temperatures. So then we got to talk about, gas to a liquid. What we call this is condensation. So it's always condensation from a gas turning into a liquid. And basically what this condensation is, right? It's the same thing. We always talk about condensation. You've got a window in the winter. It's cold outside and it's hot inside. You breathe on that window. You can basically condense you breathe on it from the outside. I mean, you can condense your breath onto the window. It goes from a solid to a liquid, and eventually that liquid freezes into a solid. So you go from a gas to a liquid, and eventually it turns into a solid. So gas to a liquid is condensation, and a liquid to a solid is freezing. So we freeze something when we turn it from a liquid to a solid. Um, yeah. So the last one, what we're going to cover is we're going to cover a gas to a solid. We call this deposition. And a solid to a gas, we call that sublimation. So sublimation is basically if we had a block of solid CO2, and you just left it in the room, you'd see it turns directly into a gas vapor above it. Whereas deposition, this could be the same thing. If the window is very, very cold in the winter and you breathe onto it, it can basically turn into ice directly onto the window. It goes, a gas, it will go through a gas to a liquid to a solid, but it looks to us as if it turns basically from a gas into a solid on that window. So now I'm just going to quickly show you how to draw these phase transition graphs, and we're going to talk about it. So basically, we draw our axes, and this we're just going to label as time, and this we're going to label as the energy. So the energy of the system. So as things, as we know, to go from a solid to a liquid, we need to heat it up. So we need to increase the energy of the system. From a liquid to a gas, we need to heat that up too. So that's increasing energy of the system. So what we're going to see is, let's do this for water first. So for water, for water, we've got 0 degrees Celsius is its freezing and melting point, and 100 degrees Celsius, 100 degrees Celsius is going to be the boiling point. So let's take away just for this circumstance, because we're doing an exact example here. And then we could generalize it later with energy. So 100 degrees Celsius, 0 degrees. So what happens, right? We take an ice cube, we cool it down. Let's say right down here is minus 25 degrees Celsius. So we heat it up. So the temperature is increasing with time. So we're heating it up. And at 0 degrees Celsius, we see an interesting thing happen. Is that we keep supplying energy to the system. We're heating up linearly. So let's just say we're just adding, we put it onto a hot plate. So we've got a hot plate, and the hot plate's at a set temperature. So let's just say this metal, we heat it up to 300 degrees Celsius. So basically, if we put something on top of that, you're heating it up the same every second. It's not 300 degrees Celsius per second, but let's just say the same amount of heat per second supplied to the system. So we're applying the same amount of heat per second. We've got this block here of ice, and we put it on top of the hot plate that's sitting at a sitting at 300 degrees Celsius and not changing. So it's applying the same amount of heat per second supplied to the system. So what we see is that we heat up, the temperature is raising, minus 24, minus 23, minus 10, minus 5. At 0, we see a plateau. Then after this plateau, for a while, the temperature keeps increasing. Then we see a plateau. And then the temperature keeps increasing after that. So this is going to be our typical graph for heating. So this is going to be our heating curve. And what we're going to label is we're going to label sections A, section B, section C, section D, and section E. So we're going to talk about what's happening in section A. In section A, right, I'm just going to erase this. I got more space actually. Hopefully you've got those words written down so that this next part makes a little bit more sense. So section A, what's occurring is that all particles, or all atoms are in the solid phase. So All atoms are in the solid phase. So if we increase the temperature, right, in the solid phase, so in solid, the only movement is vibrational. So we've got them all in the solid phase next to one another, like this. And they're all just vibrating a little bit. So they're just vibrating left and forward and up and down, and they're bumping into their neighbors. So basically, as temperature increases, the intensity of the vibrations increase. So the vibrations are becoming more and more and more intense. So basically we're creating increased vibrations, increased friction. So we're basically making them rub against each other a lot more. They're vibrating more violently left and right and left and right and left and right as temperature increases. So B, what's occurring at B, we call this the melting point. The melting point. So at the melting point, what we see from the graph is that there's no temperature change. No, so we do that delta T. So no delta T, no temperature change. And that is because all the added energy, so all the added energy from this hot plate is used to overcome the lattice energy. So we talked about the energy, we talked about them being in a solid phase. And in this solid phase, at this temperature, is that the intermolecular forces, so what the lattice energy is the forces holding these molecules together. So basically, the nucleus of one, so the nucleus of one, which is positively charged, which we're going to learn in the next unit, can be attracted to the electrons of the other one. And the electrons of the other one can be attracted to the nucleus of its neighbors. So that is the lattice energy. It's the energy of attraction. The energy of attraction between neighboring atoms. So lattice energy, the energy of attraction between neighboring atoms or molecules. Because right, sugar is a molecule. Sugar can be a solid, but when it's in a solid phase, the sugar molecules are all next to one another. It's not just atoms, so we're not just dealing with a pure metal where it's just copper atoms next to one another. We're actually dealing with more complex molecules. So the melting point is no change in temperature because all of this energy we're putting into the system is used to break this attraction between the neighboring atoms. So when you break that attraction, so basically, let me change the color to something brighter, is when the attraction is broken, the molecules or atoms can flow past one another. So before you were in a solid, we increase the vibrational energy by increasing the temperature. And at this point, you increase the temperature so much that the attraction between him being held next to, 4 different ones, or 6 different ones, because there's one in the front and one in the back, basically the attraction holding them together is reduced. So the vibrations have become so intense that he can start to flow around the solution. So he's overcome that energy holding him into place, and then now he can flow. So now that he can flow, we do section C. Section C. C is the liquid phase. So like we said in the liquid phase, basically atoms can flow past one another. So the atoms can flow past one another. And what's holding them together? We say intermolecular forces. So inter meaning between, molecular, molecules, forces are keeping them attracted to one another. So these intermolecular forces are what keeps it in the liquid phase. It keeps it, we haven't overcome that energy. So we've overcome the lattice enthalpy, the lattice energy. We're not going to talk about lattice enthalpy and stuff now until IB. But we've overcome the lattice energy, and it's breaking apart from its lattice, from the lattice structure. Lattice structure. So you have to overcome the lattice energy to go to a liquid phase. In the liquid phase, we've got these intermolecular forces. And basically, lattice energy is another way of basically just saying some sort of intermolecular force, which you're going to learn eventually. But basically, these intermolecular forces are holding this liquid together. So that these molecules are flowing past one another, but still they've got some level of attraction. So something holding them together. So for some of them, it's an attraction between the positive and negative ends. Some of them it's attraction just between the electrons that are around the atoms. But we just like to say intermolecular forces for you guys. It's just forces between molecules. Forces between molecules are keeping them attracted to one another. So basically, as the temperature increases, the energy, which we say the EK, the kinetic energy, it increases. So the liquid atoms or molecules are moving faster. So they're moving faster. So as we increase, so for C, we increase the temperature. The molecules or atoms at the top here are going to be moving a lot faster than the ones that are 1 degree Celsius down here. So they're moving a lot faster. And then at D, so let me erase this. So basically we increase the temperature, we increase the kinetic energy of the particles. So let me just erase this section over here. There we go, good enough. So for D, we've got D right here. We call this the boiling point. And this is the same thing as the melting point, is it's no temperature change. All energy is used to overcome intermolecular forces. So those forces between the molecules that are holding them together, all of the energy is used to overcome those forces. So basically, rated 100 degrees Celsius, if you imagine we've got a beaker of water, these liquid molecules have gained enough energy that they stop interacting with one another. And that's what we said with gases, right? With gases, we assume that there's no interaction at all between the atoms or molecules. So what happens is that this one right here, he gains enough kinetic energy that he can fly out of the solution. And now he's entered the gas phase. So he's turned from a liquid to a gas. He has the energy and he escapes the intermolecular forces of the solution. in order to enter the atmosphere and start to travel around in the gas phase. So all of the energy is used to overcome the intermolecular forces and convert, let me just change the color, and convert from liquid to gas phase. So that's why we see no delta T, is that all of the energy that this hot plate is pumping into the solution is only used to break the intermolecular forces. So it's not used to speed them up anymore. They're already fast, but then, you know, what's keeping them from getting faster is the fact that they're attracted to something. They're attracted to the other liquid molecules. And then at E, this is going to be the last one we do in this video. Let me just erase this real quick. And E is going to be the same thing as C and A. So A, we increase the vibration. C, we increase the kinetic energy. And E, we said, right, there's no structure in a gas. So at E, there's no structure, no set structure. It's in the gas phase. And in the gas phase, the molecules do not interact. So the molecules do not interact with one another. So all the added temperature, so all the added heat that we put into the system, you know, heat is not the same as temperature. Heat is energy, all the energy we put in, and temperature is just the average energy that the system possesses. So all the added temperature, which we're going to talk about, so all the increased temperature, which means the increased energy, is converted to kinetic energy. So higher temperature is a higher kinetic energy. So we've got faster moving gas molecules or atoms. So faster moving. That's why, you know, a steam burn, I don't know if any of you have ever had a steam burn before. You know, you get hot water on your hand, it hurts, but you get hit by hot steam, it burns extremely quickly. It really hurts. I did that just last year. So a steam burn is a lot more dangerous than liquid burn because liquid burn is limited to less than 100 degrees Celsius. A steam burn, right, we can have 300 degrees Celsius water vapor here. Vapor that just comes out and burns us with much higher, higher energy and a higher temperature. So I hope this video was useful. You must be able to draw graphs like this. You must be able to say that the parts here, right here, and right here, the word that we need to know is plateau. Is a plateau, and that's where all of the energy is used to overcome the lattice energy and overcome the intermolecular forces. And you must be able to label what happens at each section, what happens at A, B, C, D, and E. So hopefully this was useful. I will see you in the next video.